So in the previous class, we looked at the Navier-Stokes equation. We have already derived that in a series of lectures. And in the previous class, we brought everything together and gave you the form in which Navier-Stokes typically appears. And then we have left out some homework problems for you to do it for compressible as non-Newtonian fluid flows. What happens? I mean, how do we get the right form? And so something like this you can now drive for yourself. Now, after that, we started looking at tensors, and this is where we were. Now, before I coming to the class, I said, everybody, please do a small exercise. How many of you have done that? Okay, I see quite a good amount of hands, but not everybody. Why did the others not do it? This was like more than a day you had to do it, right? Anybody wants to volunteer an answer here? Yeah, that's not something very, very good. I mean, this is a very small exercise, and this is where we will start off in our lecture today. So if you have done it, it is much easier for you to follow what we are talking about. So in the previous class, we wanted to start with tensors, and we said before we get into tensors, we have to look at scalars and vectors. And scalar has magnitude, no direction, vector has magnitude and direction, and then we are going to extend that idea to two directions. So if we have 1 and 2 as the coordinate systems, 1 and 2 prime are the axis, same axis upon rotation of the coordinate system. And we said that we can write out beta ij as an angle between old I and new j. Correct? Right? This is what we had said. So therefore, this angle becomes beta 1, 1. This angle becomes beta 1, 2. This angle becomes beta 2, 2. And this angle becomes beta 2, 1. Okay, so please understand that we are simply saying that what are the axes are 1 and 2. These are the new axes. Okay, so sometimes people were, I mean, in the past, we are not, why are you not putting 2, 1 prime? Okay, so we are not putting 2, 1 prime is because it just understood that whatever. So we are denoting new with prime. So it's when you say angle between old I and new j, it is already like this I, this one, second one is already corresponding to the new coordinate system, or that after transformation, after rotation, the coordinate system that we are looking at. So, so if I take any point here, any vector here, we know that the components are in the original coordinate system. These are the components, and in the new coordinate system, these are the coordinates. And we said that we can find out x1 prime and x2 prime as in the form of a matrix, which is C12, C11, C12, C21, and C22. And this is x1 and x2. C21 here, C21 here, and C12 here. Okay, so, and if you were to extend this, so this is what we had derived in the previous class. And then we can extend this to say that x1 prime, x2 prime, and x3 prime from here can be written as C11, C21, C31, C12, C22, C32, C13, C23, and C33. X1, X2, X3. So we are simply going from here, this relation which you have derived in the homework, to this relationship here. Okay, and these things are convenient because now we don't have to bother about whatever is the angle between these two lines will be given like this. And again, a simple example has illustrated. That's why this example was important. So simple example has illustrated that this whatever we are writing is indeed correct. So now from here we are going to write, I mean, x1 prime is equal to c11 x1 plus c21 x2 plus c31 x3, which we said we can write it out using a summation with a ci1 xi and I going from 1 to 3. Okay, and similarly, if I write out x2 prime, I can write it out as summation of ci2 xi and I going from 1 to 3. And similarly, I can write out x3 prime is equal to summation of c I3 xi, I going from 1 to 3, correct? So now if I have to write out all these three equations together, what I'm seeing is that this I, this 1 is the same as this 1 here, this 2 is the same as this 2 here, okay? And similarly, this 3 is the same as this 3 here. Okay, so I'm, instead of writing it out as 1, 2, and 3, I can just write it out with another thing which is j, and say that xj prime is equal to c ij and xi, and with the summation I going from 1 to 3. Okay, so now we can see that this is, we are using tensor notation here, and this is where I will now start explaining what exactly, I mean, what are the advantages of doing it this way. So first of all, is this clear what we have done here? Very quickly, this is very straightforward. Now, there are two things. If I look at C, so you can see that there are subscripts in C and in X. So these subscripts will be called as indices. So Cij has two indices. Indices are I and j. Okay. Now, if I look at Cij on the right hand side, we have Cij xi with a summation I going from 1 to 3. So first of all, if I look at this term, what is it that I realize? I mean, there are indices on this Ci which are I and j, and there is indices on this which is I. So if I take it together, then how will I look at it? I will say that I is now appearing twice and j is appearing once. Okay, so I will say that I is a repeated index because it is appearing twice. Okay, and j is appearing only once. So let me just, I is appearing twice, or it is a repeated index, and j is appearing once, and I will call this as a free index. Now this is where we start to need to understand, this is where I'm getting into tensors now. Now what are we saying here? What is the property of I? What did we do over I? We simply summed it up, right? And how, and over what? What was the range over which I was going? 1 to 3. Where is 1 to 3 coming from? The dimensions. Okay, so this again is clear from here. Okay, we are looking at coordinates. We are looking at a physical quantity. Let us say if I'm looking at a vector as a physical quantity, it has going to have 3 components, and therefore all these x's that I'm talking about and x primes that I'm talking about are all going to have 3 components, not more than that. Okay, so that's where the physical dimension, physical thing is coming. So you can see that there is 2 information that I is carrying, which is repeated, then and for which I need to add it up, and I need to add it up from 1 to 3. But both these 2 things are obvious. Okay, I don't need to say that every time. Okay, so I don't have to say it every time. So what I'm going to do, so this was the equation that I had written. This is the equation that we have written up. So instead of that, if I now say that I'm just going to write it out as Cij xj. Cij xi. So I'm just saying, I'm omitting, what I'm saying is I'm omitting this altogether. Okay, why am I omitting this? Because I is appearing twice, and if I is appearing twice, all I need to do is simply sum it up. And sum up over how many times? 3 times. And 3 is coming from the dimensions. Okay, so that's all. So that means that I can now write out this equation in this manner. And what is J doing, by the way? J is just generating these 3 equations. So if I take J is equal to 1, I will get the first equation. If I take J is equal to 2, I will get the second equation. And if I take J is equal to 3, I will get the third equation. So J is giving me how many such equations are there. And it's a free index. Okay, so there are only 2 types of indices, and this is all there is. If you just understand these two, as simple as this, it is as simple as this. Okay, there is nothing more complicated than this. There are only 2 possibilities. One possibility is that the index appears twice, okay, which means it is a repeated index, and I need to add it up. Okay, and other possibility is that its index is appearing only once, and then it's a free index. Over. If an index appears 3 times, 4 times, n times, there's a mistake. That index, that equation does not make any sense. Okay, so there is no possibility that the index will appear more than twice. So there are only 2 possibilities, once and twice. Okay, is this understood? And we have seen from this example, okay, what are these 2 types of indices and what do we do with them? Okay, so we'll just write out these 2 simple rules. Okay, index, there are only 2 possibilities. Appears once, it's a free index, and appears twice, is a repeated index. I need to sum it up. Right? Is this clear now? Is this idea clear, first of all? Anything difficult here? No, right? So now don't start getting confused. Just keep these 2 things, simple things in mind. Now I will start showing you what all can confuse you. Okay, so what can confuse you? Can I write out this equation as xj prime is equal to ckj xk? So I am writing this equation as ckj and xk. Have I done anything different? No. Why? Because if I look at this term, k is repeated, okay, and all I have to do over the repeated index is to sum it up, and that sum will go from 1 to 3. Okay, what was I doing here? Exactly the same thing. Okay, so you can say that this repeated index is nothing but a dummy index. Appears twice, it's a dummy index. And what do I mean by that dummy index? I can always replace it by any other index I want. Okay, as far as it is not contradicting, it should not be conflicting with my free indexes. Okay, if I write it out as k, j, j, and j here, then what happens? Now the index is appearing 3 times, and that's a mistake. So now I have changed the meaning altogether. And you can see from here, if I write it out as xj prime, so what we have already seen what it means, these equations means, but if I write it out as xjj, cjj, xj, okay, so then, I mean, this is a mistake, I'm not saying that this is correct, but if I were to write it out, what am I meaning now? This is c11 x1, maybe c22 x2 plus c33 x3, and this is not what we were meaning. This is exactly, this is, all this is incorrect. We have already written the correct form here. right? So this is garbage. Okay, so this is garbage. Okay, so an index will not appear more than twice over. Okay, so that's the first rule. That's the first understanding. When it comes, you see a repeated index, that it means that I can always interchange it as far as it is not conflicting. Any other thing which I like or I find it more convenient, I can replace it with that. And the meaning of the equation will not change first. The second, what is the only rule about free indices is that when we write out an equation, the free indices on the left hand side should be the free index on the right hand side. Okay, so that's all that we need to know. So free index should be same, or let me just write into the sentence here. Free index should be same on both sides of an equation. Okay. So if I can check this, whatever we are claiming, is this equation correct? What are the free indices on the right hand side? Free index on the right hand side, J. What is the free index on the left hand side? J. Okay. What about here? Free index is J and J here again. So, I mean, it does not mean the equation is correct, but at least it means that tensorially it is not incorrect. Okay, it does not mean that everything I just because J is matching on both the sides. Don't come and say that my Navier-Stokes can be written in whatever way I want. Okay, because the J is the same on both the sides, everything is the same. Of course, that's not what we are meaning. All we are saying is that okay, at least that is not incorrect, or it may tensorially it may not be incorrect. Otherwise, we know other way to say it. If it is not matching, it is incorrect. Over. Okay, it is garbage. Whatever you have written is garbage. Okay, understood? Now, the other thing that free indices gives me is now we are getting into tensors. So now the other thing that we can say is that number of free indices is going to give me what type of a quantity we are talking about, a scalar, vector, or a tensor. Okay, so now if I see all these were vectors, as we can see, and how many free indices are there? We wrote this as, you see that what are we writing this as? Xj prime, right? All this transformation that has been shown here, this equation, this entire equation has been written in that one simple box equation, correct? And all this step is giving you how we wrote it. So the left hand side of this quantity is what? A vector. And what is that vector corresponding to? A single free index. Okay, so when we see a single free index, it's a vector. Okay, so you can see now that the index is giving you the direction, right? So you can say that this index is giving you whether we are talking about x1 or x2 or x3. Okay, so it is giving you which component are we talking about. So it is given corresponding to the direction, correct? And so if I look at this quantity Cij in itself, what is going to correspond to? Two directions. One is going to be given by I and the other one is going to be given by j. Okay, but Cij xi becomes a vector. Okay, so this is where we need to understand, because now if we are talking about Cij, the term that we are looking at Cij, and if I look at the indices, there are two free indices in Cij, I and j. If I look at Cij multiplied by xi, I am looking at only one free index. So now it becomes a vector, right? There's nothing, I mean, we are again not saying anything very difficult here, right? So we have to see whether we are looking at the term individually or we are looking at a product or whatever. Okay, so that quantity Cij itself is a second order tensor, okay, but multiplied by xi becomes a first order vector. Okay, understood? I can also multiply it. Can I do this? If I say Cij xk, Now I'm writing a different quantity, but I'm looking at tensor. Now what is this quantity? How many free indices? 3. What are these free indices? I, J, and K. So what does it mean? This is a third order tensor. That's it. So when it comes to tensor, this is a third order tensor because there are 3 free indices. Understood? Okay. So again, just look at the indices in the term, determine whether they are free indices or there are repeated indices. If they are repeated indices, all it means is you can sum it up. Okay, you don't have to do it immediately, but you can sum it up. All you need to do is sum it up, and that's a dummy index. Okay, the free indices is what you need to look at. Okay, and the free indices is going to give you the what order of a tensor is this. Okay, now if I look at CII, what is this? What is this now? How many free indices? Free indices. There is no free indices here. I and I are repeated index. Free indices is 0. So what is it? Scalar. This is a scalar. Understood? Fine. So I hope that this is clear now. So now, having introduced, so this is, we have just introduced what is a tensor, okay, and how do we determine this. Now we said that before we get into tensors, we have to understand how does a vector transform. And we said that vector transforms in this manner. It follows this rule that we have written here, okay, or this rule that we have written here. Now the good thing is that we can use this idea and extend it to how to define a formal tensor. Just like we said, a vector is not just any quantity which has one direction, but it needs to transform. So again, if we were to go back to this, what did we say? That if I am claiming any quantity to be a vector, okay, I will like to look at the components of that in an arbitrary frame of reference. Initially, I put 1 and 2, and I could have put any other way. Okay, so I just put 1 and 2 as some coordinate system, and I look at what are the components of that vector or sort of claimed vector that I'm getting. So I get x1 and I get x2 as the components, but that is not enough. Okay, so I rotate the coordinate system by any arbitrary angle. Okay, here we just say arbitrary angle is beta 1, 1. Okay, but it could be any arbitrary angle I can rotate it with. Okay, and then I get the new components, which are in this case x1 prime and x2 prime. Now once I have gotten these components and knowing this matrix in between, I say that if the new components are related to the old components in this manner, that means I find it out in this manner, and I also get whatever I've gotten earlier. Now, if the two things are comparing or are exactly correct, are matching, I mean one from whatever components I have gotten in the new coordinate system, x1 prime and x2 prime, and the other case, after rotation, doing this rotation, calculation through the rotation, I find both of them are identical, then I will say that that's a vector quantity. Understood? So that's a formal definition of a vector. Now, so if I can, I'm going to now use the same idea and see how a second order tensor will get transformed. So I will now say that again, just like any quantity with one direction is not a vector, any quantity with two directions is not going to be a tensor, a second order tensor. Okay. So if I'm looking at sigma ij, so what should I do now? How will it transform? So I'm going to use this idea itself, idea from here. So if I use a C, okay, and what is common here, I'm just trying to sort of explain to you how we write this. Whatever is index here is whatever is the first subscript here. Okay, so I will write out the first subscript, and I will say it's a K. Okay, and on the left hand side, prime, and now I'm looking at the kth component. Okay, instead of I is now becoming a k here. So I write k here, and then I put another c because I have to just, this has transformed this first direction I and mapped it into k. Okay, now I have to map this j into into a new thing. So I say that this is j, and always it's the first index here, so it's j, and then this is l. So this will now map into l here. Okay, so if you just think about it, maybe my explanation is not good enough. You can think about what we are doing. Okay, all we are saying is, if you look at the Cij, okay, the first index is the same as this index here, and the second index is the same as whatever we get on the left. Okay, the same thing we are doing here. Okay, sigma ij, the first index is whatever is the same as here, and the second index is what will map to this place. And because we are looking at the first index here, it will map to the first index here. Okay, and then the second index, when I take j, so I put with another c, okay, which is going to take this j, and then it is going to map into l. Okay, so then this l is the same as this l here. Okay, that's all. And if I know that, okay, so now what is the good thing about it? Now you can see that this is of the form ABC. In algebra, we know ABC can be written as BAC, ACB, etc., etc. So you can see that I don't have to bother about where do I put these C's. Okay, it will automatically take care of itself. Okay, so that's the one power that you can see about tensor. Okay, it is just like now it has become, earlier what we were dealing with, we were dealing with vector matrices, and we have to see whether A into B is not equal to B into A in general, as we know with matrices. So we'll have to be careful about whether we pre-multiply, post-multiply. Here we are now writing it out like an algebraic equation. An algebraic equation, ABC is the same as BAC and so many other combinations, right? So that's one advantage that you get. And then it also tells you that if I'm talking about an nth order tensor, okay, so nth order tensor could be, let us say, if I look at, there are n directions. Okay, maybe we will not try to generalize that. I think for now maybe it is too much. But in general, we can once we understand this, we can always generalize it to an nth order tensor. Okay, is this clear? Yes.
So this equation of this transformation, in this we are transforming I to K and J to L.
Yes.
By using CJL and CIK.
Correct.
This is the like one line explanation.
Correct. Can we give the general? General could be like A has n directions, which are A1, I1, I2 to In. Okay, and then I want to write an A prime here. Okay, and so what do I do? First take this I1 and change it to J1. So I write this becomes now my J1. Okay, and then I take C and then I2, J2. So this becomes a J2 subscript. And similarly, I keep on doing this and I come to C, IN, JN, and I get all the way to JN here. That's it.
There will be n summation.
There will be n times these matrices are getting multiplied n times. And that's how a nth order tensor will transform. Okay, and this is a transformation rule. So if so now again, just what was the importance of this here? We said a vector is a vector only if it satisfies this transformation rule. Okay, similarly, now we can say that a tensor will be called as a tensor only if it satisfies this transformation rule. Okay, now let us see what are we talking about here. So we will take an example now. Any questions before this? C is cosines. That's why this exercise was very important. Okay, so C is cosines, all cosines, and all cosine of the old I and the new J. That matrix is not changing. It's just that it is going to be used n times here. 2 times in this case, n times in the general case. So let us see how does the stress matrix transform. So I will start off, where do I start off with? Okay, so maybe we can check very quickly what sort of a tensorially is this equation making sense. Okay, so the term on the right hand side is this term. Okay, what sort of a term is this? What indices are here? I, J, K, L. There are 4 indices, out of which 2 are repeated and 2 are free. And we said the free indices are K and L, and that should be the same on both the sides. Okay, so at least we are passing all those rules, and though no index is appearing more than twice. So all the rules that we have said are being are passing here, are being satisfied here. So what we will do is take this sort of a transformation and see how to apply, how will the new components of a stress tensor. Now this was in general, this sigma could have been anything, any second order tensor. But now let us say that if it is the stress, how will the stress transform? Okay. So I will take some particular component of stress. Which component? I will start off with K is equal to 1, L is equal to 1. Okay, so I start off with K is equal to 1, L is equal to 1. I choose this, and I will have to do it for each component. Right? So just like we wrote out 3 equations here, you can see that I will have to write out 9. There are 9 components because K can go from 1 to 3, L can go from 1 to 3. So there are 9 components. Okay, so I will have to do it for 9 times. And for every component, I may have a different way it will transform. So I will do it for one and I will leave it for others, for you to do for others. So I'm just going to write K is equal to 1, L is equal to 1. I've just chosen it. So I put 1, 1 here. C, what do I write? What do I get on the right hand side? J is 1. No, J, what is J? We have not said anything about J. We leave J as such. L is 1. C, I. We have not said anything about I. And K is 1. And then sigma ij. Correct? So all we have done is substituted these 2 values in this equation here. Now what do I do next? Now I start expanding over I and j. Okay, and because I want to get to see the final answer, I want to now start expanding out about I and j. So if I expand out about I keep, the first term the same, 1, 1. So expanding over, or let me just say, now I'm expanding over I, C11 sigma 1j plus Cj1 C21 sigma 2j plus Cj1 C31 and sigma 3j. Correct? So what we have done is now taken this I. This I is being expanded, written as 1, 2, and 3. So you see here, okay. So this term does not change, okay. And here I have first chosen I is equal to 1. So this is 1, and the second one, this is, I also put 1 here, j here, and then I is equal to 2. So 2 comes here, I is 3, and 3 comes here. Okay. Now what is the next thing I do? Is expand it out over j. Okay. So here I'm going to make some simplification to begin with, otherwise it's going to become just too long. We realize what are the angles between 1 and 3, and what is C31 in this? I'm expanding it out over the vertical axis which is perpendicular to the board, and I'm just rotating about this axis. So 3 and 3 prime are coincidental, they are still the same, and the angle between 3 and 1 prime and 3 and 2 prime are 90 degrees. So cos of that is 0. So I don't have to bother about this term. So I can just drop out this term. Okay, and here also I will not write it out 3 terms. I will just write it out 2 terms because the other term is automatically 0. Now you have understood that. So I will expand out j. Okay, so j is C11 C12 sigma 11 plus C21 C11 sigma 12 plus. So this is what I'm getting from my first term. You can point out if there is any mistake here. Okay, please feel free to just let me know if there is a mistake. And if I look at the second term, I get C11 C21 sigma 21 plus C21 C21 and sigma 22. Yeah, sigma 22. So I hope this is correct. Okay, and all the 3's 1 and 3 terms we know that they are 0, so I have just dropped them. Okay, because they are corresponding to an angle which is 90 degrees and the cos of 90 degrees is 0. So all those terms get dropped off. So what do I get now? So what is sigma 11 prime? What is C11 now? So I will just say that this angle is alpha, beta 11 is alpha, okay, and I can find out all other angle with respect to that. So I know that C11 is cos of alpha, C12, what is C12? C12 is cos of the beta of, what is this angle? 90 plus alpha, right? And what is 90 plus alpha? Minus sin alpha. C21 is the angle of cos of 90 minus alpha, so sin alpha. C22 is cos of alpha. Is this correct? Right, I hope this is correct. So now I can come back here, I have all the C's here. So this is nothing but cos square alpha of sigma 11 plus what is this? C21 C11 is cos and sin alpha cos alpha, and this is sigma 12, and this is C11 cos, this is with a minus sign, C21 is correct, this is also with a plus sign, sin alpha cos alpha, and sigma 21 plus cos square alpha sigma 22. So does this remind you of anything? Yeah, this is your stress tensor. You were dealing with this all along, right? And you said, oh, if you just rotate it by 90 degrees, oh, sorry, what by some angle alpha, this is what you will get. This is what we are getting exactly from our whatever we have done. It's just that we have now followed a framework which is more general, and therefore we have seen where exactly it comes from. Of course, we can do it for each component. That's what we do. Okay, for area and for force, and then you say that this is what you get, which is exactly what we are doing in a more mathematical way. This is a more mathematical approach. The other one is a more physical approach. There you can see which component we are taking here, but you are getting all these things here. Okay, so what it tells you is that when you take a second order tensor and you transform that, you expect to get cos square, sin square, cos and sin terms, right? And similarly, if you are looking at nth order tensor, how does it transform? It's going to transform as cos to the power of n, sin to the power of n, cos sin to the power of n minus 1, cos sin to the power of n minus 2, and so on. So all those terms in between will also show up. Okay, and why it is coming is now very clear from this derivation, or as we know that again we are projecting each direction, and each direction is going to give you a cos and sin. And then when you take a product, you will have all sort of cross product terms. Yeah. Yeah, alpha is beta 1 1. Okay, any questions here? So I hope you are comfortable with tensors now. Certainly, yes, yeah, correct. Otherwise, you see now whatever it comes out. There also you do it in a planar thing. We never do it in a more general thing. You will get all these components also non-zero, and we have all those terms. It's just that we have thrown away as zero. Otherwise, keep all those terms as well. And in fact, then all the sine and cosine, these are also not so. There is not one single angle which is relating all of them. Okay, you'll have to worry about the other angles, and you have to look at all those causes, etc. Okay. Any other question? So we have, yeah. Okay, maybe I have made a mistake. You can just go back and check that. So okay, so sine square, sorry. I just wrote it very quickly. Thanks for pointing it out, sine square. So now you can now go back and complete this exercise for other components. I will now leave it for you. You can go back and complete it for other components. Okay, but again, when you look at an equation like this, okay, when you look at an equation like this or with the, you don't have to get worried. All you have to do is, again, just in your mind, tell what are the free indices, what are the repeated indices. Free indices, if you're looking at a component, then choose a case like what we have chosen here, okay, and then just work out over the repeated indices, whatever you get, okay. So now we'll move on, and we will just say that there are two special indices. One is a chronicle delta ij. So this is a special where I is equal to, this is 1 if I is equal to j and is equal to 0 otherwise. So this is a special tensors, and this is known as a chronicle delta. I hope my spelling is correct. Okay. Now there is only another interesting tensor, epsilon ijk. Okay, this is what type of a tensor is this? This is a third order tensor. Okay, this is a second order tensor, and that is equal to +1 if ijk is cyclic and -1 if ijk are anticyclic and 0 otherwise. So this epsilon is what is known as an alternating tensor. And what do we mean by cyclic? By cyclic, we mean that ijk are appearing as 1, 2, and 3, or are appearing as 1, 2, 3, or 2, 3, 1, or so all I'm doing is starting with from 1, 2, 3, and just taking 1 from the to the very back. Okay, so I get 2, 3, 1, and then I can take again to the back, 2 to the back, the first term to the back, so I get 3, 1, 2. Okay, and then again if I do the same, repeat it again, I will get 1, 2, 3, which is already covered here. Okay, so these are the three possibilities that I have, which are cyclic. And similarly, if I look at anticyclic, I start off with 3, 2, 1 instead of 1, 2, 3, and I repeat this exercise. So in anticyclic, ijk will appear as 3, 2, 1, and then I can repeat this exercise and I will get 3 take to the back. So I will get 2, 1, 3, and then I will take the first term again to the back. So I get 1, 3, 2. So you can see that these are the 3 possibilities where if I, j and k are occurring in this order, then then the value of this epsilon will be simply -1 in this case. Is this understood? Now, delta is easy to understand. Okay, so where do we see delta? So if I look at some examples, let me just take 1 or 2 examples. So if I look at, let us say, Vi delta Ij, so what will this become? So again, for what type of a vector is this? What type of quantity is this? Vi delta Ij is a vector, and the free indices should be j. Okay, so I can expand it out. Okay, so if I expand it out, we get, so repeated index is, so I take j is equal to 1. So let me just say j is equal to 1. So I get Vi delta I1, right? So let me just call it as arbitrary as Aj, just to sort of make it look like an equation. So I'm writing it out, the A1 term of this as this here. So I get this as, now I have to expand, this I is a repeated index. Okay, so I write it out as V1 delta 1 1 plus V2 delta 2 1 plus V3 delta 3 1, correct? And what are these quantities? 0, because of this relationship, this condition here. It's only going to be 1 only if I is equal to j, which is only the case here. Okay, so this is only V1, other plus zeros. So this is V1. Okay, so if similarly, if I take j is equal to 2, what will I pick up? V2. If I pick up take j is equal to 3, what will I pick up? V3. So what will I say? This quantity is equal to Vj, right? Because j is equal to 1 in this case, and I'm getting a V1. Okay, if j is getting 2, I'm getting V2. Okay, so this is nothing but Vj. Understood? Okay, so what does it mean? So now if I look, if I understand this, if I understand that this is how it will become, what is the rule I will say? What is my rule now? Wherever I see deltas are very nice, wherever we see delta, okay, you take this quantity and you interchange this index by whatever index is there in Ij. Okay, so that's what it becomes. So if I take, let us say, any other quantity, not just C, let us just say A. So Aik and delta Ij. Now what will I get? What will I get from here? So you can see that I will have to, this I, so just like here, this I was common. So here this I is common, and that I am replacing it with j. Okay, so same thing I'm going to do here. So this I is going to become simply Aj and k. K does not change anything, so it stays as such. Okay, so this is a very nice sort of a simplification that I can get. Okay, and we can check what sort of quantity is this. Again, it's a second order tensor here. Okay, first order vector here. If I say Aij delta Ij, what happens now? Same thing, right? What sort of a quantity is this? Scalar, no free indices. Okay, I and j are the only two indices, and both of them are repeated. So there is no free index here. It's a scalar. Okay, and what will I write it out? Same thing. I can write it out as Ajj. I can write it out as Aii. Right? Both of them mean the same thing. I know that. I can write it as AII, or I can also write it out as AJJ. Yeah.
In the second example, if it is like AJK delta IJ.
AJK, and delta IJ.
Delta I, then will it be AIK?
Yes. Now what will it become? So again, you can start off by saying what are the indices here? I, J, K. What sort of indices are here now? J is repeated, I and K are free. So at the end, I should get something which has free indices I and K. Okay, that is very clear. Otherwise, I will not get the. Otherwise, my indices are not, the free indices have to match in an equation on both the sides of the equation. All the free indices individually should match. Okay, understood? Now, where will you see this epsilon? So we have not said anything about epsilon. So now let us talk about a vector product, a cross product of vectors. So let us say that vector A is equal to vector B cross vector C. Now, how do I write this? This is what we will use by writing it as this epsilon term. So let us say if I want to write out the kth component of this. So I'm writing out the kth component of this, taking the kth component of this. Okay. And then I'm going to write it out with an epsilon ijk, because here B, okay, maybe first let me just write out and then we can explain what we are writing here. And this is going to be my AK. So look at the equation. Does it make sense? What have we done? So we are writing it out as epsilon ijk, okay, with an epsilon, because I had a B and a C here. Both of them are vector. Vector should have a one free index. Okay, so I use I here, let us say, and J here. Okay, so then with an I and J I have written here. So then I get an epsilon. I have to put an epsilon because this is going to be a vector product. This vector, after multiplying or taking the cross product, I should get a vector. So that vector should also have a free index, right? So that free index is whatever is so you can now see is, let us say, Sk. So then I need to put an epsilon here, which will take. Otherwise, if I don't write it with an epsilon, what sort of a quantity is there on the right hand side? This is not a scalar. It's a second order tensor, because what are the free indices? I and J are two free indices. So it's a second order tensor. What is there on the left hand side? Is a vector. So first of all, it is not matching. Vector and tensor, second order tensor cannot be equated. So that is garbage to begin with. And then what is further garbage? Of course, the free indices are different. There is no common free index here, even on the two sides, right? So I mean, the way this cross product is taken is that you introduce this epsilon. Okay. And then how is this epsilon taken? Now epsilon, the order of this epsilon is very important. So how has it been done? We have said this Si is the same as this index here. This index is the same as this index here. And then whatever is the free index is what I get here. Okay. So that's how I can write it out. So I mean, it is easy to write. So you can just write with B and C with whatever indices you want. Then you put an epsilon, okay, with the free index, first free index, second free index here. So now it becomes repeated indices. Both of them are becoming repeated indices. And then once you put the third index, then the same third index you have to put here. So it's simple to write, okay, but this is a simple, I mean, just trying to emphasize that this is how you can write it out. Okay, and we will see one example to sort of illustrate this. Okay, by the way, any questions here? So now with this, let us go to derivatives. Yeah. Yeah, that's what we are going to get to now. The equations, all equations, Navier-Stokes can be example written using tensor notation. Okay, so maybe we can start with this. Okay, so maybe because it's going to involve derivatives, that's exactly the topic that we are going to cover now. And then we will come back and say, how do I write continuity equation? How do I write my momentum equation? And you will see the advantage of that. First of all, it becomes very compact. And then you have all the advantages of algebra, a lot of advantages of algebra coming in there. Yeah, these are all Cartesian tensors, yes. I mean, I don't think anybody really uses them. Okay, I have never seen anybody sort of working within non-cylindrical, non-Cartesian coordinates. Okay, maybe there are, I am not aware of it. Any other question? Yeah, but this point about Cartesian coordinates was very important. I had not emphasized it enough. So we are always talking about Cartesian coordinates. I mean, whatever we have chosen are all Cartesian coordinates, and yeah, so that is like the one is underlying assumption, and we are always working in 3D space. If you look at maths where people can talk about nth space, then you will have to specify the whatever what the summation is going over. And by the way, this repeated indices that we very quickly has a very fancy name. You know what is a fancy name? It's called Einstein summation convention. Okay, so it is given to Einstein. Okay, so when we remove the summation sign and just write out without the summation sign, we say some people will start saying I'm using Einstein summation convention. So I'm not showing the summation sign explicitly, and I'm not showing explicitly that the summation is going from 1 to 3. I've omitted that, and this is where this omission is what is called as Einstein summation convention. Okay. Yeah, but as somebody remarked, Einstein had better thing to do to claim this fame for rather than just removing this summation sign. So that's why it was not introduced earlier. Okay, so any other question? So let us look at grad of phi. Now I'm looking at the derivatives and see how we look at this. So how will I write it out? It is written as dou by dou x of phi along the ith direction plus dou by dou y of phi along the jth direction plus dou by dou z of phi along the kth direction. Correct? That's how things are written. So if I have to write out this equation in tensor form, I will write it out as xj and a phi. Okay, so now j, so here now the free index has gone, all that has happened is moved from the numerator to the denominator. Okay, because it is showing that this I can talk about derivative along either the first direction or the second direction or third direction. Sometimes we call it as first, second, third. Now I hope it is very clear. Instead of calling it x, y, and z, it is easier to call it as 1, 2, 3. Okay. So if I were to call it as 3 directions, and then we are saying that whether we are talking about derivative along this direction or the second direction, third direction. So I can pick up which direction I'm looking at, and therefore, and the same thing I mean here. So I'm looking at the derivative of phi along either the first direction, the second direction, the third direction. This is also what this equation is saying, and therefore these two statements mean the same thing now, right? So having understood this, I can now say what is del dot v, which was, let us say, was the here our equation. So what will it become now? So first of all, what sort of a quantity is this? It's a scalar quantity, not a vector quantity. Okay, although v is a vector, but after taking the derivative of that, or rather the divergence of that, it becomes a scalar quantity. So how will I write it out? If I have to write out explicitly, you just say that this is dou u, dou x, as dou v, dou y. So, or if you want to again write it out maybe in 2 steps, it is essentially like a dou by dou x I plus j dou by dou y plus k dou by dou z dotted with So this is my first operator, as we have seen here. This is my first operator, and it is operating on ui plus vj plus wk. Right? So I get this is what I get. And how will I write out this equation? I have to come closer to you.
Del Vj by del x.
Del Vj by del xj. Right. So this is nothing but write it out as j del xj. Okay. So again, so here we have to understand that what we are saying is that we are looking at the, I mean, there is no free index here. J is a repeated index, no free index, it's a scalar quantity. And this derivative is corresponding to, just like this derivative is corresponding to, this is corresponding to the various directions. But then these directions are only acting on particular components. And of course, it's ultimately a sum up all of them. Yeah. No, we are not. There is no free index. There in free index we don't sum it up. So here we have to pick up one component. So if I pick up one component, okay, maybe we should write out. So this is what this is. So what is this quantity here? Right. So I'm just saying that what is the jth component of this? This is going to be essentially picked like this, just like we have picked up. So this is my vector equation, and in there I said that I'm only looking at the kth component of that. So I pick the kth component on both the sides. Okay, and then this is nothing but I write it out as this. Okay, so same thing I'm doing here. Okay, now with this understanding, let us look at the cross product. So I'm looking at, so divergence of V I can write, but now let us look at curl of V. And what is curl of velocity? Vorticity. So although we don't have to necessarily sort of relate it to vorticity at this point, it is good to sort of, so let us look at curl of velocity V. And we know that this is vorticity, or if you don't know, it does not matter. We just think of as some vectors, V as some vector, W as some vector for now, or omega as some vector for now. So I'm going to, how will I write out this equation? Omega k epsilon. So this is a cross. So I have to use an epsilon here, and epsilon I j k, and then this is going to be derivative dou by dou xi. Okay, first index here, and then a vj. Correct? So just like we had taken the cross product of B cross C, I've just taken the same thing here. So this derivative, this operator is happening first, and then this is happening. So then the same thing I'm doing. So in here, I could have interchanged this and said that this is nothing but epsilon I j k C j b I. I can write it out like this. There is nothing wrong in there, because as I said, these are ABC, and in algebra, ABC can be interchanged. Okay. So I can always write it out like this. But when it comes to derivatives, we have to be careful. We cannot interchange these two. Okay. In derivatives, it will not make sense. Okay, because its derivative is operating on a particular quantity. So here we cannot change the meaning. Okay, so you have to be careful when we take the derivatives. Okay, that's the only caution, that you cannot interchange. Here A and B are not interchangeable, or not necessarily interchangeable, or most of the time it will not be interchangeable. But in the other cases, when it is not derivative operators, then we can interchange them. Okay, but otherwise, whatever rule we have said here is being followed here as well. Okay, so we will now, look at one case and show you how to use this. So let us say I look at omega 3. So I want to look at vorticity in the third direction. Okay, so rotation about the z direction. This is omega z. So what is omega z now? So what do I do? Again, epsilon I j3 dou by dou xi and vj. This is my equation first. Okay, now what do? I expand out over repeated indices. So I'm picking j is equal to, sorry, k is equal to 3 in this case. Okay, so k is equal to 3 I picked up, left hand side I put k is equal to 3, right hand side I put k is equal to 3. Okay, so that's the first starting point. Now I just expand out over the repeated indices I and repeated index j. First I will expand it out over I and then I will expand it out over j. Of course, you can interchange the order and nothing should change, and maybe it's a good exercise, good thing that you try it once for yourself to convince yourself that this is indeed the case. So epsilon 1 j 3 dou by dou x1 of Vj plus epsilon 2 j3 dou Vj dou x2 plus epsilon 3 j3 dou Vj dou x3. Right? So all I have done is expanded out over the repeated index, which was I, and essentially I have to sum up, put I is equal to 1, 2, and 3, and sum up the 3 terms that I get. Right? Now I will do it the same thing over. So by the way, I can, before even doing further, we can know that what this is going to be, epsilon 3 j3 is always 0. Okay, because epsilon was not 0 only when I, j, and k were all different, either 1, 2, 3 or 3 to 1 or and their cyclic and anti-cyclic combination. So those are the only cases where this was not, this was, otherwise this will be 0. One can, I mean, I'm just being a little bit lazy here, or not necessarily lazy. I mean, you can just go and verify it for yourself. So here I will again do, again j is equal to 1 term, so I will expand out this term. Okay, so let us do that. 1 3 dou v1 dou x1 plus epsilon 1 2 3 dou v2 dou x1 plus epsilon 1 3 3 dou v3 dou x1 plus, so this is what I get from my first term. So this is what I get from my first term. The second term gives me epsilon 2 1 3 v1 x2 plus epsilon 2 2 3 v2 x2 plus epsilon 2 3 3 v3 x2. Okay. So now in these terms, first let us look at what are the terms which are non-zero. What about the first term? 0, because 1 is appearing twice. What about this term? Not 0. This term? 0, because 3 is appearing twice. What about this term? Non-zero. This term? 0, 2 is appearing twice. 0, because 3 is appearing twice. Okay, so what do I get? Omega 3 is equal to epsilon 1 2 3 dou v2 dou x1 plus epsilon 2 1 3 dou v1 dou x2. Correct? So this is what I get, only the two terms which are non-zero, every other term is 0. Now what is epsilon 1 2 3? 1. What is epsilon 2 1 3? minus 1, right? And of course, if you want to write out in terms of u, v, w, the component, so I can write out that omega z is equal to, this is v component, and this is going to be derivative along the x direction, the first direction, the x direction, and this is the u component, the first component of velocity, which is u, and this second direction, which is y. Right? We know this, that this is correct. Right? Everybody with me? So now, as you were asking, what is the utility of the tensor? You have just seen one utility of that. Is when we want to look at vorticity, I don't have to now remember anything. In fact, really speaking, I don't have to remember anything. I can simply get vorticity understanding by knowing this relationship. Okay, by understanding how do I work with this cross product. Okay, and I've shown that from this knowing the cross product, and of course knowing the epsilons about epsilon, and knowing whether it is cyclic, anticyclic, all these are reasonably straightforward. I mean, once you sort of do it 2-3 times, you have it. I mean, it goes into a system. It is not very much more difficult than that. Okay, any questions here? So I have given you some small homework about how to write Navier-Stokes equation in tensor notation. So I will not give out the answer here. You can go back and look at it for yourself, and maybe you can sort of comment. You should be looking at the compactness, or does it make the equation more compact or not? Things like that you can sort of look at, and maybe other advantages, whatever you see, maybe you can comment on that. So that's one thing. Now, finally, we have a few more minutes. Let us just spend a little bit more time and just look at a few generic properties of tensors, because I want to close the topic today. I don't want to linger it. I don't want to have it linger on. So, so we'll just make a few very quick comments. Maybe in the next 5 minutes, we'll overshoot by a few minutes. So let us say the addition. So remarks on tensors maybe. So if I'm looking at, can I add up two tensors? Yes, just like vectors, we can add up. Okay, but I can add up vector to a vector. I cannot add up a scalar to a vector, right? It does not make any sense. So similarly, I cannot add a first order tensor to a second order tensor, or a nth order tensor to an mth order, or a pth order tensor, right? They have to be the same order, right? So I can always write aij, for example, if I'm talking about 2 is bij plus cij. There is absolutely nothing wrong in here. This can be done. Okay, here we have to look at each term. So each term is, these are the terms b and c. Again, I have to look at the free indices. Okay, all the free indices should match on both the sides. Only then it is a meaningful equation as far as tensors goes. So I cannot add it with, for example, bjk plus cikij. This is garbage now, right? This is garbage. Why? Because b has free indices j and k, and the others have free indices I and j. Okay, so the free indices are not matching, so this equation is incorrect. Okay, so that's the simple rule about addition. I can add, and of course I cannot add up bij and a cj, for example. This is garbage again. Okay, because again the free indices are not matching. So this is incorrect. So addition and subtraction. Now we can also do inner and outer product, just like we have done earlier. So we can multiply, for example, I can multiply aij with a bij. I can, just like I multiply a scalar to a vector, I can multiply a scalar to a second order tensor or a third order tensor. Okay, that's not an issue. I can multiply tensors of different order, but I cannot add up tensors of different order. Okay, So this is fine. Okay, for example, and again, whether it is even this is fine, be let us say KL. This is also fine. Okay, here we are increasing the order. Here we are increasing the order. A and B were both second order, but taking the product has become make it as a fourth order. Here I have taken the product, but they have become a reduced order. In fact, it has become now a scalar because there is no free indices here. Okay, so I can increase the order or I can decrease the order, and we call this inner product and outer product. Just like we take inner product and outer product of vectors, we can take inner product and outer product of tensors, and we can raise the order or reduce the order. Okay, now we can talk about division. So in vectors, division exists? No. Okay, in tensors, division exists? No. Okay, so division does not make any sense. So I cannot divide two vectors, I cannot divide two tensors. Okay, and okay, I think there is one property about symmetric and anti-symmetric, I think which we will need to look at. Maybe I think we'll have to stop here. So, but this is one simple thing, that any tensor can be broken down into a symmetric and an anti-symmetric part. That's sort of an interesting in some point of view. Maybe we will just spend maybe 5 minutes in the next class, and I think then we'll be done with this topic here. So any questions before we move out? Any questions, comments? Okay, if not, we will meet next Wednesday, 1 week from now, because this Friday is a holiday and we are not having a makeup class.